Day 122, lenses and finding image locations. Here's problem example number 4, a double lens system. In the first case here, part A, the two lenses are separated by 60 centimeters. The focal length of lens number 1, f sub 1, is 20 centimeters. Focal length of lens number 2, f sub 2, is 10 centimeters. We have an object that's roughly, well, it's 32 centimeters from the first lens. I really won't be drawing a whole lot of ray diagrams of double lens systems. This problem will be solved mostly by computation. For example, in part A here, I'm just going to apply my 1 over f sub 1 equals 1 over p sub 1 plus 1 over q sub 1. In this case, for lens number 1, ignoring lens number 2, basically what you're going to be doing is finding the image of lens number 1, and that will become the object of lens number 2. Otherwise, basically everything stays the same, but obviously also it becomes more complicated when you have to go through multiple steps like this. Anyway, 1 over f sub 1, that's 1 over 20, equals 1 over 32 plus 1 over q sub 1. Plug into your calculator. Q sub 1, according to my calculations, comes out to be 53 centimeters. That's an important number, but not the final answer. I'm going to circle that just for reference right now. And I'm also going to compute m sub 1 separately from m sub 2 for the second mirror, or second lens. So it's negative 53 divided by 32. So m sub 1, the magnification of the first mirror, is negative 1.7. If the second lens weren't there, I would draw the entire ray diagram. But bottom line is that the first image is a real image flipped, almost 2 times as big as the object, 53 centimeters from the first lens. Once again, if you want to draw the ray diagram, you can, but sometimes that complicates the double lens system. But roughly speaking, 53 centimeters from the first lens is almost all the way to the second lens. It would be an image that looks something like this. It's going to be almost twice as big as the original object, 1.7 times, and flipped upside down. All right, so what happens here now then for this system is that becomes the object of the second lens. So now what we have is 1 over f sub 2 equals 1 over p sub 2 plus 1 over q sub 2. And as we see here, f sub 2 is tenths, so we have 1 over 10 equals 1 over p sub 2. Well, p sub 2 we determined from the first part of the problem. As we saw from the first part of the problem, this was 53 centimeters. Q, number 1, q sub 1 was 53 centimeters from the first lens, and the two lenses are separated by 60 centimeters, so simply 60 minus 53 is 7, so the image is, that first image, which becomes the object of the second lens, is 7 centimeters from the second lens. In other words, P2 is 7 centimeters. That's 1 over 7 plus 1 over q sub 2. Computing that, q sub 2, and calculating that, q sub 2 turns out to be negative 23 centimeters, which will be an important number. We'll talk about that again in a minute. But m sub 2, the magnification of the second lens, is the opposite of negative 23 divided by 7. So m sub 2 is 3.3. And the way you figure this out now for the total magnification, the magnification total, m sub t, t stands for total magnification, is equal to m sub 1 times m sub 2, which is basically, well, negative 1.7 times 3.3. So m total, the total magnification, turns out to be 5.6. The final image is 5.6 times bigger than the first object. Now, I gave you the initial diagram there. What turns out then, if you kind of put the pieces together, and I don't need the diagram, what I have over here circled is all I'm looking for, and specifically a reference to the total magnification and the final location of the image. But let's be a little bit more specific with this number right here. Where is that? That's 23 centimeters to the left of the second lens. Or in other words, basically, 37 centimeters to the right of the first lens. So it's between the two lenses, not quite halfway between, but you should make some reference that this Q sub 2, the final image, is 23 centimeters left of the second lens. 23 centimeters left of lens 2. Lens sub 2. Second lens. All right, now if you want to try to draw this, you don't have to do this, but the second lens doesn't flip it. It's basically a virtual image for the second lens, but the second magnification was 3.3, and this is going to look a little strange. That's why I don't normally do this, but the rough location is right about here, and 3.3 times bigger than that first image, and almost 6 times bigger than the initial object. So your image would look something like that. You don't need to draw that, however. Let's do one more example here. All right, this problem starts off the same way. The difference is that the separation distance now is 40 centimeters. I'll change this to 40 magically. And the object starts in the same spot as it did before, 32 centimeters. So what happens here is the first lens functions the same way it did before. So all the initial computations are the same as it was last time. So I'll just fill those in again. You can look back at them. So the first image, once again, the rule is this. The image of the first lens becomes the object of the second lens. But here something kind of interesting happens. We're sort of ignoring the second lens here for the time being, because this first image will actually not be what happens, but it's a tool here that we'll be using. The image here is now going to be this first image is to the right of the second lens, 13 centimeters, because we need to get to 53 centimeters. This distance has to be 53 centimeters, which is 13 centimeters greater than the 40 centimeter separation. So this first image, with its magnification like we had before, the magnification number 1 was 53 over the 32, which was a magnification of 1.7, negative 1.7. That's how big it was magnified the first time. Nothing has changed so far for this first lens. We're still ignoring the second lens for the time being. This image would look something like this, almost 2 times the size of the object, but it's 13 centimeters to the right of that second lens. So now here's where things are a little bit different than part A, or actually we're doing part B now. I should maybe change this to a B. We're going to continue on with the second lens. So we have 1 over f sub 2 equals 1 over p sub 2 plus 1 over q sub 2. Well, f sub 2 is still 10 centimeters. Equals, now here's where the one exception to the rule where p will always be positive, the only time we're going to have a negative object distance is when we have a double lens system. And here's the one time when p is negative. In this case, it's negative 13 centimeters. It's on the right-hand side of that lens, according to our convention here. So that's a negative 13. So plus 1 over q2. So we have the negative object distance. Putting that in the calculator, we get q sub 2 equals 5.7 centimeters. And what does that mean? Well, let's calculate the magnification first. M sub 2 now will be negative 5.7 over the 13, which is 0.44, negative 0.44. Sorry, check that. This 13 down here should have been a negative. So the magnification becomes positive. M sub 2 is positive 0.44. Got to remember to put that negative 13 in there. That's important in this problem. So there's our second magnification. So the magnification total, once again, will just be the product of M1 times M sub 2. So the magnification total is going to be negative 1.7 times 0.44. So the total magnification is negative 0.75. I should say negative 0.75. That's what that says. All right, so what happens here is the final image then is actually going to be smaller than the original object. It's about half the size of the first image, but it is a positive distance from Q2, or lens number 2. It's 5.7 centimeters right of the second lens. So it looks something like this. Not a whole lot different than the object, but it's going to be small and right here. A little bit smaller than the original object, about half the size of the first image. So that's our final object. You don't need to draw that, but to give the full answer then, you would say something to the effect of, what's the final location? 5.7 centimeters to the right. 5.7 centimeters to the right. Of lens 2, the second lens. M total is negative 75. It's like 75% of its original height. And that's how we describe the final answer for a problem with two lenses.